video with the three alkali metals, lithium, sodium, and potassium, right? Now what we're going to do in this video, we're going to talk about the periodic trends, okay, down a group, and you can look at that video. I'll pop it in the description, the link in the description, so you can watch that, okay? But definitely we're looking at down a group in terms of periodic trends. Okay, so periodic trends down a group. Okay? Now, all you have to do, folks, all right, is this. We're going to do this, okay, to represent our group or family. Now, I'm only going to use 3 boxes, yes? Okay. Now, the first box up here is going to be for lithium, right? Now, from experience, right, lithium has 3 protons, okay, and an electron configuration of 2-1. It has 2 electrons in the first energy level and 1 electron in its valence shell. Now, since this is group 1, people, all right, it's group 1, all of these guys are going to have 1 valence electron. So lithium has what? 3 protons in the nucleus, okay, and 2 shells, okay? So there's a little number 2 there outside it. That's what that means. Period 2, right across, okay? Those guys have 2 shells, okay? In period 3, alrighty, okay, you have sodium, right, under lithium. And sodium has 11 protons, okay? And his configuration is 2-8-1, okay? So 2-8-1. So once again, 2 electrons in the first energy level, 8 in the second, and 1 in the last, okay? 1 in the last. So all the guys in group 1 have 1 valence electron, okay? Alrighty. And in period 4, okay, under sodium, so this is Na, and this is Li, okay, we have potassium. And potassium has 19 protons, okay, atomic number 19, okay, and his electron configuration happens to be 2-8-8-1. 2-8-8-1. What does that mean? And so you guys can see. Okay, in the first energy level, alrighty, he has 2 electrons. In the second energy level, he has 8 electrons. In the third energy level, he has 8 electrons. And the last one, he has 1. So notice, right, all these guys have 1 electron in the valence shell. As we go down, okay, the group, progressively, we notice, right, the number of protons is increasing. So, you got the protons are increasing, all right, the valence electrons are the same. So you might think, right, yay, since the protons are increasing, the attraction should increase, right? But before we even say that the attraction is increasing as we go down, we have to analyze 2 things that affect attraction, right? And we agreed the attraction that we're talking about, the coulombic attraction that we're talking about, is between the protons in the nucleus and the valence electrons. The protons in the nucleus and the valence electrons, protons in the nucleus and the valence electrons, people. Okay, so here's the deal. In the analogy we did before, we agreed, right, in terms of having a relationship with someone, you would rather be close to them in the same building as opposed to being a whole like world apart from you, in other continents someplace, right? So for our purposes, right, and for coulombic attraction, distance, increased distance, all right? So increased, INC for short, increased distance weakens attraction. So hopefully that makes sense. Okay, so the further apart the charges are, the less attraction there will be, okay? And there's another factor, right, that we talked about that weakens attraction, and that is what? That's called the shielding effect. We said, right, let's say the protons and are looking at their valence electrons with a certain desire and wants to be attracted to them. These guys in between, these energy levels in between, are blocking or they are shielding the attraction that the protons in the nucleus have for the valence electrons, that the protons in the nucleus have for the valence electrons. So if you notice, right, it's called the shielding effect, right? As we go progressively down, we notice this guy right here has one energy level, okay, blocking the valence shell. These guys have two energy levels, two shells, blocking the valence shell. Now in potassium now, guys, you have three shells, okay, that are blocking the valence shell in terms of the attraction between the protons in the nucleus and the valence electrons. If you notice for potassium also, he also has what? He also has the most distance between his protons in the nucleus and the valence electrons. So potassium has two things that are working against him. He has increased distance, okay, between the protons in the nucleus and the valence electrons, and he has a shielding effect because he has more principal energy levels, or just energy levels, right, between the protons in the nucleus, right, and the valence electrons, the VEs. Okay, so how is that going to affect our trends, people? So let's look at that right now. Try to move over gently. Okay, so what I'm going to do, folks, I'm going to use shorthand, okay? All right, so you got four trends, right? AR. AR stands for atomic radius, right? You got MC. MC stands for metallic character, all right? You have IE, ionization energy, and we have EN, electronegativity, right? Okay, so let's go over here. We're going down the group. We agreed our attraction is getting weaker because of these two factors right here, the increased distance and the shielding effect. So now you got to answer these four guys right here. Now the funny thing, folks, attraction in this topic of trends rules everything, right? Now the most obvious simple guy to figure out in terms of going down a group is atomic radius. Because you look at these guys right here, there are more and more shells as you progressively go down. Okay, lithium has only 2 shells, sodium has 3 shells, okay, and potassium has 4 shells, okay? So he's getting larger and larger. Think of the shells as like coats of electron cloud, okay? So as you go down a group, right, your atomic radius increases. You put a little arrow up next to it, your atomic radius increases. Now, in terms of metallic character, right, I like to explain it as, you know, behaving like a metal, all right, metallic character. And we know from experience metals want to lose electrons, yes? So, when you go down this group, right, the shielding and the distance, right, that potassium has, right, makes potassium's attraction weaker, alrighty? So, when we did the experiment, right, we saw that potassium almost caught on fire right away and was very, very reactive, right? That means his valence electron is released very quickly and he reacts with anything around it to achieve a stable octet. So the metallic character of potassium is greater than these other guys above it. And if you go further down below potassium, you get to guys like cesium and francium, those guys are incredibly reactive, okay? So you should Google it and see, you know, how reactive they are, okay? So as you go down the group, your metallic character increases. Why? Because the attraction decreases and the valence electron is easily released, okay? So metallic character also increases. Alrighty, ionization energy. The energy needed to remove an electron off the valence shell. Sometimes say loosely held electron on the gas, but you know, we don't get too technical with that. So once again, if I try to pull an electron, the valence electron off of lithium, right, versus trying to pull it off potassium, right, which one's going to come off more easily? Think about it. So we agreed, right, that potassium has what? has weaker attraction, weaker ATT, right? The weaker attraction. Okay? All right, write it over here. Weaker attraction for potassium, very important. Okay, because of what? Because of shielding, because of increased distance. So if I come along and try and pull this valence electron off, it comes off much more easily, okay, until I put less effort and much energy to take it off than I would for lithium. So as you go down a group, right, what happens is your ionization energy decreases. The energy I need to remove a valence electron is much easier to remove a valence electron. It decreases. Okay, last one, electronegativity. The ability to attract electrons towards yourself in a chemical bond. Now, we know metals, right, overall don't like to attract electrons toward themselves. Okay, they want to lose electrons, right, lose their valence electrons. But in terms of the ability to do that, okay, who has a stronger attraction? We agree that as you go down, right, once again, because of what? The increased distance, because of shielding, especially, okay, the electronegativity, folks, the ability to attract electrons toward yourself will decrease, okay? Because why? The attraction is decreasing. There's more shielding, okay, that causes, that blocks the attraction the proton has for a valence electron. So the electronegativity decreases as you go down a group because of the weakened attraction. So once again, real quick, atomic radius increases, all right? There's less attraction between the protons and the valence shell. Plus, there's more and more shells, so that, it gets bigger. Metallic character increases. Why? Because it's easier for the guys as you go down to release their valence electron to act like metals. Why? Because of weakened attraction. Okay. Ionization energy decreases. Why? Because it does not take that much energy to take the guys that are lower in the group than the higher guys. The lower guys in the group have weaker attraction. The valence electron comes off more easily. You take less energy to remove it. The electronegativity, okay, also decreases. Why? Because of shielding and increased distance. The guys that are lower in the group have weakened attraction and are not able to what? Attract electrons towards themselves as much as something that's higher in the group. All right, guys. Take care.